Hello, everyone. My name is David. Today, I'll talk about our work, UnifiedTensor, enabling GPU-centric data access for efficient large graph GNN training. This work was mainly targeting for training a very large graph, which is usually not fitting into GPU memory. So let's just talk about working with large data sets. In general, dealing with large data set is very tedious because the implementation was not assuming for such case. For example, you were used to working on some small data set, so you can quickly do some of the parameter searches. And then later you try to grow your data set and you realize some of the code was not fitting because you assumed something was fitting into GPU memory. And second, you try to just simply move it to the CPU memory, and then now you realize fetching data from slower storage like CPU memory affects the overall training time. So that's so far just in general working with a large data set, but actually in terms of GNN, when dealing with a large graph is even more tedious because now the data is sparse and accessed in a fine-grained manner. So this impacts a lot in terms of performance and the complexity of your code when the data cannot be fed into the GPU memory and it must be stored in the CPU. So this is the current approach, or at least how behind the scene, how the things weren't working. When the data set is stored in the CPU, for example, like a node feature tensor, and the data access needs to be kind of scattered around because of the graph data structure. Then what CPU does is actually read the scattered data from its own memory and write it into the contiguous buffer, and then DMA being sent to the GPU. The reason is DMA engine cannot deal with complex data access pattern, but rather more simple, something like contiguous access or some strided access. Therefore, if there's some kind of a data dependent access using graph structure, these indices needs to be used by CPU to gather it first and then create the temporal buffer. By using CPU together, the performance and perform bulk transfer, there are two issues. Well, the first is a question of scalability with multiple GPUs. For example, right now we have only one CPU, or let's say one CPU socket. But if there is a growing number of GPU, then it means each CPU socket needs to deal with more data transfers to provide the data to the GPUs in the right time. And second, there's a resource contention at the host side. Again, the CPU will be now start to be a throttle or the bottleneck of the whole data transfer during the training. Or just to simplify, explain, host memory bandwidth requirement increased by 3 times in this case. For example, CPU need to first read and write, and DMA read is being done by GPU. So in this case, statistically speaking, to send a 1 byte of data, that you need to actually access the host memory 3 bytes time. So what this means is, for example, let's say if you want to maintain or fully utilize the PCI bandwidth between CPU and GPU, in case of PCI Gen 4, it's about the practical bandwidth is about 24 gigabyte per second. And it means because the data access needs to be done 3 times, averagely we need to sustain 72 gigabytes of host memory bandwidth to keep the PCI bandwidth at 24 gigabyte per second. And let's just assume if the GPU, there are like 8 GPUs in a node, then this means the total bandwidth that the host memory should be able to provide is going over 500 gigabyte per second. And so far, there are no such system which can provide such a high host memory bandwidth. So the alternative solution that we suggest in this work is a zero copy access from GPU, which makes the GPU as a data center of the data access. Instead of CPU gathering behind the scene the data for the GPU, GPU can actually access the host memory directly using zero copy access. In this case, CPU simply needs to pass the IDs of the node to the GPU, and GPU will use those IDs to directly access the host memory. In this case, CPU does not need to read or write and make a contiguous buffer, such a temporal buffer. In this case, we can significantly reduce the resource because now, again, there's the previous mentioned problem of 3 times of data rating is gone. So now before we actually start to apply the zero copy access, I'll briefly talk about the mechanism of zero copy access. The zero copy access, even if it's going to the host memory, the underlying mechanism is not so different from the regular GPU memory access, which means if you can identify a qualous access, then it can generate a larger memory request instead of many smaller memory requests, which will increase the efficiency of memory request access. For example, in this case, we're showing three cases. The first is the strided access, and the second is merged and aligned, and the third is merged but misaligned data access patterns. The strided access pattern, basically, even if there is a even if there is a spatial locality, you're ignoring it and you're just intentionally accessing in a larger stride, and there's no spatial locality detected in this case. In this case, underlying the hardware, what happened is actually that all the requests are chopped into the smaller 32-byte requests, and the PCI request also goes down to the 32-byte request. This means the number of the PCI requests that you generate to access the same amount of data increases significantly. Because each PCI request requires some of the header information, this increases the portion of the header or the efficiency of the PCI request dramatically goes down. As you can see the diagram at the bottom, the PCI bandwidth in this case is only about 4.74 gigabyte per second. However, now you identify a contiguous data access pattern, and all the threads in a warp are, let's say, accessing a contiguous space. In this case, the individual 32-byte request, which was fragmented before, can be actually merged to 128 byte automatically by the GPU. In this case, the PCI request also becomes 128 byte, thus the per PCI header portion reduces significantly. And as you can see, the bandwidth also jumps to 12.23 gigabyte per second. By the way, this result was measured in using PCI Gen 3, and that's why it's currently the bandwidth is kept to 12.23 gigabyte per second. But here, one thing needs to be careful is even if your request is contiguous and merged, still, if it's misaligned to the GPU cache line, which is 128 byte, data access can be still fragmented. For example, in this case, intentionally, I skewed the memory access alignment a bit. And in this case, because if the two different warps are accessed in the contiguous data set, this can be still fragmented to 32 byte and 96 byte. As you can see at the diagram at the bottom, in this case, because still the data requests are fragmented, the bandwidth achieved is dropped to 9.4 gigabyte per second. So in short, actually, if you can just follow a regular rule of data access with GPU, for example, merge and align and a qualous access, the zero copy access over PCI can actually achieve very high bandwidth. So here's a quick evaluation of using zero copy access over the existing CPU-based method using DGL. In this case, we run the graph stage example with OGB and papers 100 million, and the test was done in a DGX A100 with 8 A100 GPUs, up to 8 A100 GPUs. So when we're training with a single GPU, the CPU-based method is taking about 170 seconds. But as soon as we use a zero copy access, the training time per epoch drops to about 80 seconds. This is about 2.02 times the speed up. But what's more interesting is if we increase the number of workers or the GPU, the speed up goes up to the 2.66 times instead of 2.02. The reason is, as I said before, because with increasing number of GPU, CPU becomes the bottleneck. Because now CPU needs to handle many more data transfer for more GPUs, but yet the amount of resource for the CPU hasn't increased. Now the CPU start to throttle back, throttle the whole training process. But in our case, now the workload of the data access has been distributed over multiple GPUs, and the GPU are the center of data access. This means we can have much better scalability in terms of our workloads. So in the beginning of the title, I said about the unified tensor. So for the zero copy, why do we need a new tensor for this? The reason is the framework like PyTorch tensor model strictly binds the location of data access and the processing unit. For example, if it's a CPU tensor, the data is in the CPU memory and it is accessed by CPU. If it's a GPU tensor, the data is in GPU memory and accessed by GPU as well. This means in the current framework, the data which is in CPU memory cannot be directly accessed by GPU. To do this, always there should be explicit data copies, for example, using DMA engine, which should be transferred to the GPU memory, and then finally GPU can access. While we keep the data in the CPU memory, GPU cannot access in the current setup. So this is the reason why we introduced a new tensor called Unified Tensor for the DGL framework. In the bottom table, we show a brief summary of what's happening. Again, if the context is the CPU, the processor is CPU, and the data location is CPU. If the context is GPU or CUDA tensor, processor must be GPU, and the data location must be in the GPU memory. Now, the DGL unified tensor breaks this binding requirement, and in a unified tensor, the data can be actually located in the CPU, and GPU will simply directly access it through the over the PCI link. So here's a bit of summary of unified tensor, what it does. The purpose of introducing unified tensor, of course, is just to allow the direct access from GPU, but is also to allow seamless and transparent integration of zero copy access to DGL, which we'll show in a later slide. In this case, the unified tensor will just look like a regular tensor, so it doesn't need to require it doesn't require the majority of users to modify their code. And second, some of the property of zero copy access is zero copy access does not require specialized hardware. A general gaming GPU even will be sufficient, such as like a GTX or RTX class from the NVIDIA GPUs. Even though we use a DGX A100, which is a Tesla grade, but we also we initially work on this work with the RTX 3090, which is a regular gaming GPU. So even most of the user with a regular desktop user can get benefit from this approach. But still, third, the data set should be fit into CPU memory because GPU cannot access those stores directly yet. Here's a more detailed mechanism of unified tensor. So currently, this unified tensor is already upstream to the DGL, and this can be called by using dgl.contrib.unifiedTensor. So here's more concrete example. Let's say you get some data set by calling certain function, and this will return a CPU tensor. To convert the CPU tensor into the unified tensor, you simply need to call dgl.contrib.unifiedTensor, pass a CPU tensor, and specify device where you want to map this CPU tensor to. For example, in this case, we are just using default CUDA device. So this, assuming there's only one device in your system, this the one GPU that you have will get a mapping to the CPU tensor, so the GPU can directly access the data stored in the CPU now. So with the return the unified tensor, unified tensor, let's compare between the CPU tensor operation and unified tensor. For the CPU tensor, let's say you just pass some indices, something like 0, 1, 2, 3, 4. Then the output, of course, will be the result of the 0, 1, 2, 3, 3, 4 row of the CPU tensor. And this will be located in the CPU as well. But with the unified tensor, you can pass indices just identical to CPU tensor like 0, 1, 2, 3, 4. But actually, the gathering or this access is now being done by GPU rather than the CPU, and the output will be automatically located in that device that you announce in the declaration unified tensor. In this case, behind the scene, the GPU is actually going over the PCI link and accessing directly the data stored in the CPU and putting it to its own memory. So on the right side, I show a diagram of in case of what if there's a multiple GPU devices. In this case, the host shared memory holds the original node feature data, and this shared memory space is mapped into the multiple devices using unified tensor classes. And each GPU or each trainer can access unified tensor separately. So each GPU needs to hold its own representation of unified tensor, and single unified tensor cannot be used for multiple device. Each device should have its own unified tensor declaration among its trainer program. So there are some more potential future directions like supporting writes. Right now, we're mostly focusing on read. And the reason might be like to extend the usage to the node embedding as well, which is frequently written during some of the training algorithms. And the last is asynchronous operation with CUDA MPS. In this case, we can use a CUDA MPS to assign only a certain amount of GPU resource for zero copy, but yet leave some of the majority part of the GPU resource for training purpose. For example, in our research work, actually we try like maybe giving 10% of GPU resource for just zero copy and 90% for the training. In this case, without hindering each other too much, they can work asynchronously and overlap the data transfer and the training. Thank you for listening, and please email to the bottom address or contact David Min7 through GitHub if you have any questions. Thank you.
Could you give me a little bit in liberation about why MPS is required? Because you can do asynchronous without MPS.
Yes, actually, that's a good question. Yeah, so the reason is actually if you just launch a zero copy access to the, and let's say you assume training kernel and your zero copy access both at the same time, then the zero copy access actually can take up the whole GPU resource and does not give any room for training. That's what we experience when we're working on it. So this MPS is to really physically throttle down to really say to zero copy kernel, like don't use more than 10%.
I see. Thanks.
Yeah, that works. So actually, if you follow our paper, and I can give you the link separately, but actually if you just naively launch two kernels in the same time, the one kernel can completely block the other one. And in that case, obviously asynchronous operation is not achieved.
Appreciate it. Thanks.
Right, yeah. Are there any questions?
Yeah. Have you looked at any of the MIG features on the newer GPUs, like being able to split the GPU physically into smaller GPUs?
Oh yeah, actually, so that's actually an interesting thing. So I did talk with or actually not even necessary. I mean, I also consulted with another NVIDIA engineer previously. But the thing is, I think you're talking about the, I forgot the exact name of it, but there was with the A100, you can actually virtualize GPU to multiple instances. The problem is actually different instances cannot share the address space between, even if they are both using the same GPU memory. So in that case, the one instance, for example, is dedicated for zero copy access, but it cannot pass its data to the different instance.
Okay, thank you.
Yeah, even if it's physically located in GPU memory, but there's no way to, I mean, I think it's more of a current limitation. I'm not sure if it's like a hardware limitation. It might be possible in the future, but right now that's a thing.
Are you saying it's not possible to pass essentially the same pointer, or you can't even do a peer-to-peer copy between the two
you cannot
instances?
do the peer-to-peer. That was a reason.
Okay.
But in the what is it? It's just the MPS is another way of partitioning. But in case of MPS, you can actually do with the IPC, CUDA IPC API, which allows the different kernels to share the virtual address within the same GPU's memory.
Yeah, that's a double-edged sword. You get good security and isolation with the multiple virtual, but that you can't share. Yeah.
Yes, that is correct. So that was a reason. But yeah, actually, that's a good point. But it doesn't mean the MPS is not supported in the newer generation of hardware. The newer generation hardware actually supports both MPS and that hard partitioning. Yep. Are there any questions? Okay, if there isn't, I think this is end of my presentation. Thank you everyone for attending.
Thank you, David. Any other questions? We do have a few minutes.
Just wanted to say it was a great talk. Thank you.
Thank you.
Great. So next we have James Zhang from the Shanghai from our Shanghai lab, and he'll be presenting the challenges and thinkings in go to production of GNNs. So James, it's yours.
Okay, thanks, Wenming, and hello everybody. This is James from the AWS Shanghai AI Lab, and I'm very honored to have this chance to talk about those things I have been facing during the process of helping our customers to adopt GN in their production environment. And even some of them didn't have I didn't get the chance to go production, but still it's kind of like end-to-end POC. So yeah, yeah. First, let me play this game. Okay. Hello. Just as I said, actually, my role at the lab is a data scientist, and my job is mainly to help the customers of AWS to adopt the machine learning and especially the GN related technology. So in the past few years, I get these opportunities to actually working with customer and help them from the very beginning to adopt the GN and all the way along to the end of full production. So today, I'm gonna talk about the challenges I've been facing during those projects, and from a practitioner's perspective, especially from 4 points of view about how to adapt a GN in the actually customer environment in a real world. So that's the 4 perspectives I'm listing here. It's from the data, the model, the solution architecture, and the explainability. Yeah, actually, very differently from like the academia domain. Normally, the first kind of challenge or questions I got actually is related to the graph data. So many times I need to answer this question: do your graph data contain enough information in order to use the graph neural network or even any graph-related machine learning technologies? So you can see that commonly in the academia domain, the research paper or researchers use those standardized graph data like the Cora, Satsia, and PubMed. And from this visualization, we can see that normally those kind of data sets are very standard and well connected in terms of graph connectivity, and this label are kind of balanced and well labeled. So I think this is good for academia research because based on those standardized data set, people can compare their method apple by apple instead of apple by banana. But actually, out of the academia domain in the real world, normally this is kind of like a graph data I got during those projects. Due to some limitation, I cannot show you the real customers' data. But here is a demo or somehow like a representation of most of the data I've been working with. Actually, in the real world, due to the limitation about the data collection or some like government regulations, we cannot have a lot of opportunity to get the full connected or well-connected graph data. Many data are very sparse. So you can see that with those sparse data, normally our GN model may not work well as we did in the academia domain. So you can see that in this demo, graph, there are a lot of dumbbell shape, just means that we only have one link connected to two nodes and without any other connections. And also in the real world data, the label is very expensive to calculate. So normally this is a real customer data. Actually, I pick 4 of them, and you can see that there are only a few of them have labels as I showed here. And also the even networks I show here actually are coming from 4 nodes, and on the top row you can see that actually one is labeled as 0 and one is labeled as 1 for the center nodes. So it's quite common that we can see that even with label, actually the architecture or the graph structure is very similar for the different labels nodes. So it's very hard to actually find a way to see whether this is good data or not, because of the exploratory data analysis can normally show us some of the real world graph data actually very similar to each other. So this make me thinking about these questions or this slogan, because in the in general, in the machine learning domain, we have this slogan or kind of like a tenet that the data determined the upbound of model's performance, and our models only just approach the upbound as close as possible. So when we go to the graph domain, I would like to change this sentence with this term: information of graph determines the upbound of the model performance, and our GNN model or other graph-related model can just approach the upbound as close as possible. Then this makes me thinking about what kind of a few questions we need to answer. I mean, in both of the academia domain and the practitioner domain. The first one is, what's the information of the graph? Since I use the term or the definition of the information of graph. So it's hard to say. Maybe just like I showed before, the sparsity which I used in one customer is the number of nodes versus the number of edges in a graph. If that number is larger, that means the graph is sparse. But do we have other like quantified indicator about information in a graph? How to quantify the structure, the graph structure or graph even structure patterns that can be used for the graph neural network or other graph related models. And even we have the way to quantify them, and how to use those quantified metrics to guide our design or use of GNN model. Which one is better for like GCN, or which one is better to use GAT or other state-of-the-art models. So I didn't see too much works actually give me this guideline. And even the most fundamental question is, when should we use graph data instead of the traditional tabular data or traditional tabular feature-based models? Actually, I got this question quite often from the customer side, because I need to answer this. Even we have a good graph with enough information, and I commonly get this kind of question. Actually, our customers somehow have been using machine learning models in their business case, and they normally will ask me, in what case are GNN model better than other machine learning models other than the graph itself? So actually, many times our customers do have some knowledge about graph neural network. So they will ask me, what kind of models should we use for our graph? I mean, so for their graph, they have their business case, they have their specific business scenario and their graph data. They want me to give them this guideline. So that's kind of a tough question. You can see that these actually are quite, I cited from one of the research paper from Stanford University's Jian group. And they actually give this design space for a simple homogeneous graph GN model. And even with this simple design space, it actually have more than 64 dimensionalities to design a common GN model. And but we all know that the design spaces could be much larger than these design spaces. So that means normally the practitioner need to pick up what kind of design decision or makes what kind of design decision for the customer data. The second thing is that even we can have this design decision for the specific business case or the customer's business scenario, and which one is better or which one is most suitable to their case. This is a very tough question. And also because DGL actually is based on the message passing programming paradigm, and can this only, sometimes people, I mean, the customer ask me this question, do we have other like paradigm can use instead of message passing? Just like this year's KDD Cup competition, the winner actually used transformer instead of message passing method on the final data to get the best result. And even I can answer those questions. Actually, there's one more harsh question I need to face before actually can help our customer adopt the GN model or GN technology. Actually, they are good at the traditional like feature-based models like charge boost, cat boost, or what kind of boosting method or other method. They say, okay, our model is outperform the GN model I proposed. But one good news is that I can answer this question somehow, because many times our customers don't have like don't enjoy the rich feature they can collect, because many of the data nodes in real world are actually featureless due to the limitation about data collection or other regulations. And so in that case, if we can take advantage of the graph connectivity and the GN will work for that case, then it could be a good choice to pick up graph-based models compared with the XGBoost. And so in that case, I would thinking about some of the questions that the research domain and the practitioner domain should work together to figure out. The one is that when we should use the GN model instead of the other kind of models like feature-based models. And the second one would be most useful. If I can get a GN model versus the business case mapping sheet or even a cheat sheet, that would be a very good guideline for practitioners to help customers adopt the GN model and use them in the real world business case. And also currently, just like I said, for the bow examples, actually I use a trick about the skip jump to outperform the XGBoost model. But whether that is a good way to use features of node and edge, because GN take advantage of leverage both graph structure and node and edge features in one model instead of separate model. But sometimes they're going to have this over smoothing problem. So that's still a very challenging topic for me, at least, is about how to leverage the feature of node and edge. And currently, I can see that GNN model may work very well for those connectivities like the graph structure and extract information and turn them into embeddings for each node or edge. But how can I combine the GNN model with other machine learning models like the feature-based model? They're very good at using high dimension features, especially the categorical features, and can we combine them together to get even better performance for our customers? That is another question. So actually, if we want to have our GN model go production, many of the time the customer can ask me to do a real-time performance, a real-time inference, because in many business cases, they want to have a real-time inference capability to actually help them capture like frosters or other or like recommendations in real time. And so to actually have the real-time inference, normally we not only need to have an inductive GNN model, we also need to have the ability to insert and extract an EagleNet for the inductive model to do real-time inference. So that actually requires the capability in the whole pipeline, the whole end-to-end data processing pipeline to adopt for to be actually adaptive to the real-time inference structure. For example, like we need to have a real-time data pipeline to get the data in, and we want to have the data persistent either in the memory or in the disk, so that we can start to build connected relations among the new added nodes with other existing entities. And after that, we need to extract the Eagle network in a short amount of time, and then set them into the model for inference, then present the result out. So you can see that it's not only about a model, it's actually a question related to the whole data pipeline if we want to have a real-time inference. Currently, many research papers use either transactive model or like a batch inference method, but that's not very useful in the real-world case. So actually, I list some of the questions or challenges here. It may not be the research topic for like a gene or machine learning researchers, but I do hope that like researchers in this domain can think about beyond their model only to help see if we can extend in the data pipeline for real-time GN model inference. And also for some system researchers, do we have fast enough graph database to insert and extract the Eagle network? And for practitioners, actually, the architecture design for real-time inference is another challenge. I didn't see very good reference architecture available for this kind of topic. And also, because I have the background about big data, we can see that in the big data domain for tablet data, we do have like a very good streaming architecture and tools to collect data in real time and batching them or streaming them into the machine learning pipeline. But so far, I haven't seen any graph-based streaming tools and solutions. So I hope we do have this opportunity to think about if we can create another like a graph-based streaming tools, for example, like Kafka or other streaming, like Spark streaming tools, to help to perform the real-time inference. And the final challenge actually I'm working with is the expandability in the GN domain, because of like even string because in common years, actually many governments actually set this regulation about like privacy or equity or others to help to prevent the AI models or AI industry from like abuse customers. So I can see that in recent years, we need to have like a model explanation before actually can put the model go to production. Unfortunately, I can find out some of the research paper and the research works about explainability on graph neural network, and this deck is kind of like a paper in this deck is kind of out of date. I collect them in the beginning of the year. However, even it's kind of like a good topic in research domain. Actually, I didn't find quite a lot practice in the industry domain. The only one I can find is actually a paper called X fraud, which was shown on the right side of the deck. I call it a semi-industrial work because actually it's kind of a paper written by one group of research from the Switch ETU and another group of practitioners from the eBay.com. I would say that this is currently the only study actually use when the Jian explained the method in real-world data actually would only report. We can see that it has a nice visualization about a fraud detection case in eBay, but that's the only one I can find. And so far in the real world, to explain the Jian result, actually in this deck, I show a demo graph. I omit a lot of information from the customer data. And you can see that on the left side of the deck, it's a two-hop subgraph from a heterogeneous graph with a fan-out 2020, which means that the model itself only have two Jian layers. And the thickness of age in this subgraph actually showing how important an age or the nodes connected to the age is actually important to the prediction result for the node in the center. Actually, the node in the center is the node to be explained. When I show this diagram to the customers people, actually it makes no sense to them. Because they can directly see that, okay, the one-hop neighbor actually contributes the most important feature to the target nodes, which should be, and why that's an explanation. Actually, it's very hard to give them a satisfied explanation from this. Not only because that in real-world data, normally the number of nodes and age is huge, even with this small number of fan-out. Visually, it's overwhelming. It's hard for them to actually explore the data to figure out a meaningful explanation. Another thing is that different from the research paper, which normally have ground truth of explanation, in real-world data, we didn't have ground truth. So in many cases, the user of the GN model need to explore the explainability result in many cases and generate the hypothesis about why the GN model predict some of the nodes or give some of the result predictions. And it's not like you recall seeing some of the ground truths. Instead, actually, it's more or less like you need to it's not like you recognize some of the ground truths you already know. Instead, you need to explore many of the cases and try to generate because of this pattern or that kind of structured information. We need to, we may come out of this explanation about the users, about the predictions. So actually, I'm working on this topic, and this is some of the questions for the research domain to answer, is that can GN model and result be explained? Even we see some of the paper, but I didn't convince that we can explain the model or result with current technology. Actually, just like I said, for the real world data, to explain the result of a GN model, it may take a lot of time for the researcher or people to interactively working with the result in many cases and explore them to generate the final hypothesis about why some of the pattern may help to explain the result. So currently there's no dedicated tools to do that work. And the next question actually is come from our customer. and also my personal experience. I can see many of the research paper give this explainability or explanation method, but who should use that? In real world business case, normally the person at the call center, the customer call center, is the person first responsible about the complaint from our customer to say, hey, why you deny my credit card application? And so should those call center person answer the question with the explainability method or explainability tools? It's highly impossible. And then that raises the question, who should make the explanation? Should this be the business analyst or the data scientist, just like I did, because I created the model and showed the explanatory result, or should it be the algorithm engineer to do that work? So I do hope that in the research domain, if we have some new explainability method or models can come out, then who should use that and give the final explanation? That's going to be one of the questions I think is most important for the research domain to think about. If only the author can use that method, then that method really makes no sense to real world case. So I think there's still a lot of things to talk about the explainability domain, but I hope that these questions can help raise help raise attention for the whole academia domain to think about them. So that's kind of all of the my presentation, and thank you. So any questions?
Hey, thanks, James. Yeah, so James has a lot of experience working with customers in China on GNN. So in some ways, we looked at across our overall customers for DGL. We actually see there are more activities happening in China at the moment than it is in the US for in terms of the sophistications of using graph neural networks. So it's really great to have James to be here and give this talk. So if you have any questions, definitely feel free to ask him, and we can have a discussion here.
Hi, this is Tristan from NVIDIA. Fantastic presentation, a lot of insights about the questions. I am new to the GNN. I'm more on the CV and NLP side for deal framework. I wonder, like being NVIDIA, we do computations and communications among different nodes. Like among all those questions, what do you think that company NVIDIA can help in some domain, like real time, something we might think about? What kind of thing do you think that NVIDIA can help most?
Yeah, thanks, Tristan. And I think that's a good question. Actually, I think in terms of your question, this four question would be somehow like in my mind that NVIDIA might help to answer. For example, like could you build up like a graph-based streaming tools to help quickly like turn many of the data from tabular structure into graph structure. For example, like quickly extract the entity and the relations among the tabular data and turn them into graph structure, and even make them only available either in CPU memory or GPU memory, so that we can process them in real time for customer, and only later on persist them into disk space. I think that will be a challenge work. So far, I've been thinking on this.
Thanks.
Any other questions?
Hi, this is Joe from NVIDIA also. So is there a way of doing an ensemble model, right? Maybe we can do a hybrid approach where we can link some graph features with something much more explainable, like a tree model. Has anyone tried that?
I didn't see research paper on that topic actually.
Yeah, I know a lot of people use GNNs just to generate embeddings, and then do the final classification with a XGBoost or a CatBoost, and then they run Shapley values to get explainability on the tree itself.
Yeah. And yeah, I think Uber actually did that kind of use that kind of trick, but still the question remains because the expectation of our customer actually is about, okay, you might help me to find out specific patterns in the graph structure. For example, like you can see that in that specific motif, if I can see that specific motif occurred in our customers' relations, then maybe it's an indicator about a fraudster group. So their expectation is like this. So if we only give them this embedding extract from the graph via neural network, and they may not be satisfied with kind of, okay, this is important feature, but what's the story behind this embedding? Could you give me the explanation of kind of like
that's a great point.
Something?
Yeah, absolutely. Yeah, the embedding hides a lot of information, right? Yeah.
Yeah, actually, we need to explain the embedding itself instead of only the embedding. All right, if there's no more questions, I think that's the end of my presentation, and thank you so much.
Well, thank you, James. Very much appreciate it. And it's also a national holiday in Shanghai, and he had to get up at 7 o'clock to do the presentation for us. So very much appreciate it. Thank you, James. Have a good rest of the holiday there.
Sure, thank you.
So I think that concludes our presentations today. If there is any topics or anything else that people would like to discuss, I'll be here, or I'll open up the floor if there's any questions, or if you feel like there are topics you'd like us to cover for the next user group meeting, I'll be very happy to find those talks. If not, you can also just email Grace and I, and my email is very simple. It's just wye@amazon.com. Yeah, I'll just put that in the chat window. Oops. Let's see, everyone at amazon.com. Yeah, and sounds like we're good. Yeah, again, I want to thank everybody for attending, and I'll see everyone next time. And before that, if you need to reach me, feel free to find everyone here is on the Slack channel. So feel free to reach out to pretty much everyone on the Slack channel, or just go to general channel and post a message there. And we'll see everyone next time.
Thank you.
Thank you, Lemmy.
Yeah.
Thanks, everyone.
Yeah,
Thanks very
thanks a lot.
much.
Yeah. And I do see, let's see, so you wanted link to the let me actually send a link to the Slack channel real quick. So let's see, I'll invite other people, copy. So Sajid, I have the link for you for the invitation. So just click on the link and you should be able to